What about it?
I was somebody.
I think it's recorded now.
Recorded?
No, I think because there's a label recording.
Oh.
Hold on, it's coming. It seems, yeah, it's okay now.
Okay, so let me continue. So the goal of my talk is to talk about the relationship between two approaches to understand the central problem in logarithmic CFT, and is the failure of the modular invariance of the characters or traces. So we know that there is a classical result in 1996 by Zhu, which stated that if V is a C2 cofinite VOA and rational, so these are two technical conditions, which basically C2 cofinite will mean that you have some finiteness conditions, which ensure, for example, that the category of VOA module is a finite abelian category. C2 cofinite itself only implies this finiteness, but does not imply the semi-simpleness. But if you assume also the rationality, then we will have a semi-simple category. And then you so Drew proved that all these the traces, these characters, or more generally these one-point functions defined by the traces, they span in modular invariant vector spaces whose dimension is equal to the number of irreducibles in this category. And this result fails if you remove the rationality. If you work with some C2 cofinite but irrational VOAs, then it will turn out that you cannot get modular invariance just by considering the usual characters. You have to consider the pseudo characters or the pseudo traces in order to recover this modular invariance property. So in 2004, Miyamoto he proved a version of this modular invariance in terms of the so-called pseudo Q trace or pseudo trace. So whose definition? So in my talk I will use the later simplified version of pseudo trace due to Erika and Nagatomo in 2011. Omega. So this is a symbol that I will introduce later. So just give you some the general idea about what I'm going to say, but I will introduce all these definitions later. So don't worry about it. It's just a more general way to construct the one-point functions on the torus. Okay, so so I will show you all these definitions later. But anyway, so what I want to talk is that this pseudo trace is a more vertex algebraic method of treating this modular invariance property. But we also have the more categorical or topological field theory way in terms of the ends and coends to the Liouvashchenko ends and coends to study this modular invariance property. So the goal of my talk is to propose a theory on VOA conformal blocks that can relate these two approaches to the modular invariance property. So in the first part of my talk, I will show you how the end and coends arise naturally from the conformal blocks theory of VOA. And in the second part, I will show you how to relate it to the pseudo traces. Okay, so first let me set up some notations. So as I said before, I will always assume my VOA is C2 cofinite and plus a minor assumption called n-graded VOA. And I will work with as you see, I work with a compact Riemann surface with n mark points. And by the way, here, although in this picture I draw it as a connected Riemann surface, but in general I allow some disjoint components of compact Riemann surface without boundaries. And I put some mark points, and for each mark point, like x1, x2, and x3, for each mark point, I pick a local analytic coordinate, and in order to talk about the conformal block, I will associate a V tensor n module W to these mark points in order. So there is a choice of ordering of these mark points, and associated to these mark points, I can attach a module of V tensor n. But I think at this point, I need to compare my convention with the convention that we have seen in York's talk. So in York's talk on conformal block, well, basically, if you have a compact Riemann surface, you have some points. For example, I draw 4 points. So we put in York's talk probably we put some V modules, so M1, M2, M3, and M4 to these mark points. For example, if you work with the Virasoro algebra, then you put some Virasoro modules to these 4 mark points. So this setting is related to my setting in an obvious way, is that I take my W to be the tensor product of all these things. So it's clear that in this picture, this is a module of V tensor 4. The reason that I consider this more general setting is that, so first of all, there are modules of V tensor n which cannot be written as in this way, or a tensor product of or a direct sum of modules in this way. And second, it is important to consider the modules of V tensor n which are not written in this way. For example, if you want to consider full CFT, if you work with full CFT, you have to consider V tensor 2 modules. These are the state spaces for example, if you want to consider state spaces for the full CFT, then you will consider it will correspond to they are described by modules of V tensor 2, which typically cannot be written as a direct sum of tensor products of V modules. So I have to consider this more general setting. So it's very crucial to consider this than the more general than this setting here. So I have this data, then I can define what is a conformal block, which is a linear map, a linear functional on this V tensor n module, satisfying some invariant property, and this invariant property is quite technical, so I won't record here, but there are some examples. For example, if you take your VOA to be Virasoro algebra, then this is what we have seen in York's lectures. But anyway, we have this definition, and this invariance property depends on the complex analytic data of my compact Riemann surface, and I will use this symbol to denote the space of conformal blocks associated to this data. These are finite dimensional vector spaces due to the C2 cofiniteness, and the dimension is independent of the complex structure and the locations of the mark points. It only depends on the topological data due to some constructions of the connections on the conformal block bundles. Okay. So here, let me introduce some more notations. So sometimes I would split my mark point into 2 groups. For example, some of the mark points are put on the left and some of the mark points are put on the right. Then I can consider, I think in this picture, this just means I consider W tensor n module. So here on the left-hand side, there are 3 points. So W is a V tensor 3 module. On the right-hand side, it is V tensor 2 module. So this, you can apply the previous construction of conformal block to this setting, but I will prefer to understand it in this way, or instead I will change you see that in this picture, all the arrows are coming inside, but I can reverse the arrow to going outside, and I replace M with M prime. M prime is the contributed module of M. So basically, if you understand this in this way, then you can basically view the conformal block as a linear map from W to certain algebraic completion of M prime. So you basically view it as a linear operator, linear map, which suggests that you can, for example, take compositions of conformal blocks just as taking products of intertwining operators. Okay, so it's important to know that the conformal block function is a left exact functor, and there is a categorical result which says that it says that any left exact linear functor from a finite C linear category to the category of complex finite dimensional vector spaces is always representable. So it means, so this will implies that if you fix this W and you consider this as a left exact functor of M, then this functor as a functor of M is represented by some object, which I called it to be box tensor W. This is the fusion product of, this is called the fusion product of W along this setting of this map of this Riemann surface with 3 input points and 2 mark point points. Okay, so this is in some sense a generalization of the Von-Epoxy-Jones definition of fusion tensor product. Their definition certainly can also be rephrased in this way. And there is a canonical choice of conformal block. I mean, if you look at this natural equivalence, and if you take your M to be box tensor W, then here both the source and the targets are box tensor W. And on the right hand side, if you take the element to be the identity map from box tensor W to box tensor W, then it corresponds to a conformal block, which is called the canonical conformal block. It is represented by this picture. Okay, and sometimes, as I said, you can view originally I define any conformal block as a linear functional, but you can also view it as a linear map from W to the algebraic completion of this box tensor W. Okay, yeah.
You're using finiteness of this category of modules over V, so you're restricting to the categories of representation. So you're just restricting to the VOAs, which will have this finite.
Yeah, I mean, when you work with C2 cofinite, there are many equivalent conditions to imply this finiteness. Well, but the so-called gradient restricted modules or finitely generated admissive modules, there are many equivalent ways to. But anyway, these are finite.
Well, so in what sense finite then? It's just like finite number of simple objects? Or?
Yeah, this category has a finite number of simple objects because it's a finite building category.
Okay.
Yeah. Okay, so here are some examples. So the top one is the one that we all familiar with. This is Von-Epoxy-Jones category, which if the input modules are W1 tensor W2, W1 and W2 are V modules, and the output is the Von-Epoxy-Jones fusion product of W1 and W2. Okay, but you can kind of reverse this construction. You kind of view the second one as the adjoint of the first one. If you put in one input module, one input points, and you take 2 output points, then this construction is first studied by Haisheng Li. Haisheng Li called this the regular representation. But for my talk, the more interesting constructions are the second, the third and the fourth one. But as I will show you shortly, the third one is okay. Here there are no input points, so it means that you need to consider the V tensor 0 modules. But V tensor 0 module is just vector spaces over C, so it means that you can just for the incoming module you can just put the complex field, and the output, as I written here, the fusion product of C, the scalar field C, is a V tensor 2 module. This is as I will show you later, it could be represented in the end in this way. And the last one is that is the genus 1 version, which with 0 input and 1 output. As I will show you, this is related to the Lukashenko's coend. Okay, and since I have already mentioned this end and coend, so let me give a review of the definition of end and coends in the setting of VOA. Let D be a category, and F I consider to a bifunctor mod V tensor n times mod V tensor n to D to be a covariant bifunctor. Then there is a version of dinatural transformations, which means that, well, A is a object inside D, and a family. So a dinatural transformation is a family of morphism. The family is indexed by all the objects inside category. So it means that for each object, you have a morphism, and you can talk about whether this family of morphisms is dinatural or not. So technically, it is defined. The property of dinatural is described by the commutativity of this diagram. Okay, so this this is one version of dinatural, but you can also reverse the order to get another version of dinatural transformations. And if you consider these terminal objects satisfying the previous dinatural property, then it is called an end. So the end is a particular object A inside my category D together with a family of morphisms, which is terminal with respect to this dinatural property. This gives you the definition of end, and if you reverse the order, you will get the coend. But in my talk, I will mainly use the end to explain some of the phenomena related to modular invariance. Okay. Okay. So here is a natural way that end and coend, the ends appears in the context of VOA conformal blocks. It is that, okay, so let's just consider the conformal blocks with 0 inputs and 2 outputs, but here I put in the outgoing module X and incoming module Y. So basically you can easily show that this space of conformal block could be identified once you choose the local coordinates correctly. You can identify this space of conformal blocks as the space of homomorphism from the module Y to the module X, where Y and X are both V modules. And as I said, the notion of fusion product, the box tensor C, it represents this conformal block, right? So it means that box tensor C is the unique up to equivalence object such that this homomorphism, this functor, represents this functor. Okay, so it is the unique up to isomorphism objects implementing this natural isomorphism where the left-hand side is the same as this one. Okay, so this first paragraph is just copying the previous definition in the context of this special case of the Riemann sphere. Okay, and you see this picture, and you notice that if you choose X and Y to be the same object M, and then the left-hand side is just the endomorphism algebra of M, and you can take the identity morphism. So on the left-hand side, I take it to be the identity morphism of M. It corresponds to a morphism on the right-hand side, so which I call the pi M. If you use a map, a morphism, a V tensor 2 module morphism from this fusion product box tensor C to M tensor M prime, and you can show that this collection of morphism, this family indexed by all modules of V satisfies the dinatural property. So this is dinatural. And moreover, you can show that by using the result of Fuchs-Stroman and Christoph, it's not hard to show that any object representing this functor is isomorphic, is indeed an end. Together with this dinatural transformation, it is an end. So that's why the thing that I show you, the guy that with 0 input and 1 output is an end. And in this way, I also show you how this dinatural transformation is defined.
Sorry.
Yeah.
Yeah, just to make contact with terminology we heard in other talks. I mean, does this have something to do with the rigidity of this category?
No, so far no rigidity. This is I don't need a finite abelian categories. I don't need any rigidity. So it also applies to for example, the Gainutdinov category. Yeah. But at this point, it only deal with these abelian theories. I haven't yet used anything about the monoidal product. All these things are only related to the abelian category, the linear structures of the category. So there's nothing about rigidity or not, right? So because I haven't used any Huang-Lebos-John's fusion product to define this thing. To define this, you don't need Huang-Lebos-John's tensor product. And to define the right-hand side, you also don't need the monoidal product of the category. Okay, so nothing to do about the rigidity at this point. And in fact, in all my talk, they apply to the modular Riemann quadratic radical categories, which are the categories of a C2 cofinite irrational VOAs.
So you're just using this dual, which is a good deal.
Yeah. So let me move on. Okay, so so here is a
That point exists.
sorry,
It's finite.
it's a finite category. So
M is
Mod is
okay.
finite.
Yeah, finite being
Okay,
calibrated,
okay,
so
okay,
basically.
Finite categories, it does exist, the
Oh,
formula
yeah.
is something.
Yeah, you're right. As object, yes.
Yeah.
Yes, yes.
So here is one of the main results that I established with my collaborator in this arXiv paper, which is what we call the Sony factorization theorem. Okay, basically what it says is it tells you how a higher genus conformal block is related to the lower genus conformal block. So basically it says, okay, you look at the right-hand side. It says that if you put an incoming module W and an outgoing module M, then any conformal block of this type could be written in a unique way as the composition of the conformal block of this type and the conformal block of this type. So you can here, this one is defined in terms of the representability of the conformal block, left-hand side conformal block function. So as I said before, I have a canonical conformal block. You can take the composition of maps between this map as a map from W to the algebraic completion of box tensor W with the map from box tensor W to the algebraic completion of M. You can consider this composition. And this composition, if you fix this one, then this composition gives you a linear isomorphism from this space of conformal blocks to this space of conformal block. And in particular, when you talk about this composition, you have to care about the convergence, just as when you talk about the products or iterates of interrunning operators or VOAs, you have to care about the convergence. Here you have to deal with the same issues, and this convergence property was proved by us in a previous paper last year. But anyway, what this tells you in particular, it tells you that the lesson here is that first of all, once you have this picture, you can always represent a half of this picture, the green part, the green shaded area with the module.
Sorry.
Yeah.
We don't understand what you mean by convergence. Does it mean that you do not have a problem that, arising from the fact that you're ending in the algebraic completion? Or...
Yeah. Basically, it's like this. Like when you take the composition, you have to first work with each graded subspace, and you take the sum. When you take the sum, it converges absolutely.
In which sense?
I mean, it's a series. So when you take the composition, you first take the composition with at each graded component in the intermediate space. You look at each graded subspace, and you restrict this map, the codomain of this map, to each graded subspace, which is finite dimensional. You restrict this map, the domain of this map, to each graded subspace, which is also finite dimensional. So when you restrict to finite dimensional subspace, these two maps could be composed, and then you take the sum over all these graded subspace, and this sum as a series, it converges absolutely.
Okay, so your definition of composition is rather tricky.
I mean, basically it's the same as the composition of intertwining operators, like the products of intertwining operators. So the idea is clear, but if you care some details, yes, these are some subtleties in order to define it, to make sense the definition of the composition. Yeah. But anyway, it not only, so by the way, it not only converges, we also need to show it is also a non-trivial part to show that it is not only convergent, but the limit of this convergence is also a conformal block on the right-hand side. So it means that once you have this map sends the left-hand side also to a conformal block, but not just an arbitrary linear map or linear functional. Okay, but anyway, what this theorem tells us is that first of all, whenever you have the right-hand side, you can represent one half of this by the fusion product of W. This is one lesson that we learn from this theorem. The second lesson is that basically it tells you that higher genus conformal blocks could be written as the composition of lower genus conformal blocks. So let me give you an example.
And your theorem does not need rigidity.
No need rigidity, just no self-dual, no rigidity for any C2 cofinite. For example, it applies to WQP algebras.
I'm wondering, would a special case of this imply the associativity of the?
Yes, this is what I'm going to tell you now. is that if you consider, maybe I write it as a whole instead of as a punctures, you can look at this. This conformal block could be represented. So this in particular, it says that it is, let's say this is M1, this is M1, this is M2. Then it gives you this M1, M2, and this box tensor. This is M1 box tensor M2 in the sense of one Lepofsky John. It factors in this way. So every conformal block of this type could be written in a unique way as the composition of the canonical conformal block and another conformal block. Okay, so this is a, and if you, so this is, if you, this happens if you decompose it in this way, but you can also decompose it in another way. If you decompose it in the vertical way, what you get is this one. And here, this is also a von Lepofsky-John's fusion product of these two modules. And so the equivalence between the composition of these two conformal blocks and the composition of these two conformal blocks is roughly the associativity of the von Lepofsky-John's vector extensor category.
And is there somewhere the Lie product?
Sorry?
You had some also this tensor product due to Lie. Is this somewhere in
No. This is the, so this is all two inputs and one outputs.
Yes.
If you consider Lie's tensor product, you have to consider one input and two outputs. Or
that's on the lower pair of pairs.
Because I fixed this one, the fusion product is on this side. So on the bottom side, I don't need to consider fusion product. It's just you consider this is basically interrunning operators of 3-point conformal blocks.
Just to connect to the talk this morning, what you called convergence is in the talk this morning. There was a sum of our Young diagrams. Remy was explaining that this converge. This is equivalent, I suppose, in your case.
You mean what equivalent? Okay, can you say a question again?
In the talk this morning, Remy was explained for you the block was converging was when you compose two points.
Yeah.
You have a sum of our Young diagrams.
Yeah. You mean the fusion kernel or something like? Is it?
Just there was 2 points. You sew them, then you have a conformal block for each one, you compose them, and then you have the sum of our Young diagrams.
Yeah. But here.
Yeah, but I just want to connect. This is the.
Okay, but here, if you take the sum, you have to. So in this setting, because it's non-semi-simple, so you don't really, you cannot just naively like take the direct sum or direct integrals. So there are some other ways to. So the fusion product here is a more algebraic notion that that plays the same role as the direct sum or direct integrals of some modules. Is that what? Do I answer your question?
If I can comment, I think so. If you're in the semi-simple situation here and C2 cofinates may be rational, then what this is doing is you pick a basis, dual basis in one of these modules, which is not a Brummer module, but some quotient, but never mind, and then you sum over basis, dual basis pair.
Yeah.
Yeah, so it's equivalent. I think it's the same.
Yeah, for rational case, is it
equivalent? It's corresponding one.
Yeah. So this is how it specifies to the associativity, but here is another example that is not as familiar as the associativity. Is that if I consider, let's say, this picture with 0 input and 1 output, which I call it to be M, I can decompose it in this way, which means that I can write any conformal on any of this type of torus conformal block in terms of the composition of this type with outgoing module box tensor C and another conformal block of this type. Okay. So you can decompose it in this way, but you can also so you see that in this picture you cut it vertically. You can also imagine cut it in this way. You cut it into the front half and the half behind half. Then what I mean is that you could get, I draw this circle, and it's hard to draw the picture, but basically another circle like this, you put it, you cut it in this way to divide it into two parts. Then you also have another way to decompose it into the composition of general zero conformal blocks. And this, the equivalence of these two decompositions is the model invariance, one version of the model invariance in the genus one setting. And it is, so here it is important to note that this fusion product cannot be written as a direct sum of, so this is not, it cannot be written as something like this. Okay. So that's why, so if you only consider modules like this, then taking the composition will only give you the usual traces, but not the pseudo-traces. The pseudo-traces that are not the usual traces corresponds precisely to these bi-modules that cannot be written as a direct sum of m times m prime. And by the way, this is also the
Yes, there's some problem with your adapter. Or
what device?
you should have 38 seconds.
But it's not the laptop, let's see.
Maybe is this my
Your device will turn off automatically.
Is this?
It's okay,
But this was not shown in my laptop. It's only
that's
here, but
so-
maybe this is not my device alarm, but other. Maybe that one.
This
or-
camera here.
I have another question.
Oh, yeah.
So this morning, Remy explained the convergence, something like this. What can you? Is it possible to summarize what argument you use to prove convergence in your case?
Prove what? Prove.
The convergence.
Uh,
What is the key fact which show convergence?
prove. Sorry, I still can't understand. So prove.
What is the key fact
Uh-huh.
which allow you to prove convergence?
A convergence. Basically, it's you need to derive the differential equations with simple poles to prove it. You use the C2 cofiniteness to derive a differential equations.
So you prove there are solution of a certain ODE.
Yeah, exactly. I have to consider connections, and I derive some differential equations and prove that it has simple poles. Yeah. Okay. So, this is turned off. Is it? Okay.
Yeah, but I mean, on Zoom it's still going on.
Okay, that's good. So, so this space is actually so you see that this is a V-tensor 2 module. And this space is actually the state space of the full CFT of Cardi type. So this type of state space cannot be written in this way. So you see that it's not only important in order to study the model invariance, it is also important for the construction of the full CFT. Okay. So this is, so as you see, this is one difference from here, because here you only need to consider V modules, but here you have to consider V tensor 2 modules. Okay, so these are the two very important special cases of the Slowing factorization theorem. Okay, so this is another actually equivalent version of the Slowing factorization theorem, which basically the idea that what it says is that the fusion product, the composition of two fusion products is also a fusion product. So the more precise statement is this. You look at this picture, you put in the incoming module W, what you get is an outcoming module box tensor W. Okay, so this is the fusion product of this object. And you consider this object as the fusion product, as the input of this Riemann surface, and you consider its fusion product. The fusion product of this one is, by definition, it's the box tensor Y of box tensor X of W. So this is the composition of fusion products. And it turns out that the previous Slowing factorization theorem is equivalent to the fact that, first of all, this module, this object, the composition of two fusion products is the fusion products of this glued Riemann surface. Okay, so this is at the level of objects, but at the level of conformal block, we also have this. We have that the canonical conformal block associated to this object is equivalent to the composition of this canonical conformal block and this canonical conformal block. So this is another equivalent. It's not hard to show that these two versions of the Slowing factorization theorem are equivalent, but I prefer to call this version the transitivity of fusion products. Okay, so these two results are very crucial for me to explain the model invariance property in for C2 covalent VOA in a systematic way. Okay, so let me come back. Let me show you how to relate it to some more categorical approach. So let us record that. Let us recall. I just erased it, but this one is box tensor C. Okay, this one is the end. This is a V tensor 2 module. It is indeed an end, and there is we can consider the Lyapunov construction, which originally was defined in this way for finite tensor category. But if you consider categories, projective categories results rigidity, you have to slightly modify this definition. You have to define it in this way. You first define the end in the Deligne product. So this is actually a Deligne product according to a recent result by Robert. And it also apply the monoidal functor to this object in the Deligne product. And what you get is a object inside the category of V modules. So this is, I think, is first introduced. This generalized version of Lyapunov construction, I think, is first introduced by Brochet and Voika. But anyway, we have this. We know that basically the Lyapunov construction is just applying the monoidal functor to this object, because this is the end in the Deligne product, right? So now you see, this is a fusion product. This is the box tensor C. And this is also a box tensor. So we have the composition of two box tensor. And as I said previously, according to the transitivity of fusion product, the composition of two fusion product is also a fusion product. So here you see, this is one fusion product. And so this is the fusion product that gives you the end in the Deligne product of two copies of representing category of VOA. And this is the monoidal product, and it composes till you get this one. And according to the transitivity of fusion product, you know that this is basically the same as the fusion product of the scalar field C along the torus. So in conclusion, the transitivity of fusion product will tell us that the Lyapunov construction is isomorphic to the box tensor of C along the torus. But let us recall the definition of the left-hand side. Any box tensor C, any fusion product is defined in terms of the representability of the conformal block functor. More precisely, this is the unique object such that which implements the natural isomorphism between this functor and this functor, right? So it means that, okay, you can replace this box tensor C with L. So what you get is that the Hom space from L to N is naturally isomorphic to the torus conformal block with one outgoing mark points N. So I think the right hand side is how the genus 1 module functors as a linear functor as a vector space is defined in the category in the TFT context. And so the right hand side is the TFT definition of the genus 1 module functor, and the left hand side is the VOA version. And our theorem, this corollary of our solving factorization theorem, tells you that you have this natural equivalence defined in terms of the composition of conformal blocks.
Is this requiring the rigidity in this case?
No. And it applies, for example, to WQP, so no rigidity.
In here, left hand side is depends on the point and the local coordinate. Is that true?
Yeah, depends on local coordinate, but the but the local coordinates does not affect. So for any two choice of local coordinates, you always have some natural but not necessarily canonical but natural equivalence by using the change of coordinates form operators defined by
it has in general monodromy, right?
Yes. So this isomorphism is natural but not canonical. You have to when you define this, you have to choose how you have to determine how it's cut it into two halves. You have to determine whether you cut it in this way or in that way. These two ways will give you two different isomorphisms, and these two isomorphisms are related by the S transforms.
Okay. So just a natural but non-canonical.
Yeah. Okay. Yeah.
So here, this also allows to deal with case with Kac-Moody symmetry or W algebra and things like this, or is Virasoro? This type of conformal block?
the W algebra, you
Yeah, does it contain conformal block of Kac-Moody? Or is
I
it just
mean,
because you didn't really say what's the definition of conformal block? You said it satisfies certain relation.
yeah, it defined in terms of the VOA structure.
But
So
you need that conformal blocks are finite dimensional.
C2 cofiniteness.
Yeah, but because you need that space of conformal blocks is finite dimensional.
Yeah.
Otherwise, nothing is working here.
Yeah, exactly.
And the category should be
Yeah.
finite, so it
Yeah.
will not
Yeah.
work with
But
it.
So it's not no.
So for example,
Fine, no, it's
yeah, but Kac-Moody SU2, this would be true.
on positive level.
On a positive
It's
level.
semi-simple, yes.
Ah.
But if it's not semi-simple, it's infinite.
Yeah.
No, nothing is working.
Yeah, exactly.
The stability goes.
By the way, who proved it that space of conformal blocks is finite dimensional for C2 conformal?
The first
For any surface, it's finite dimensional.
for C2 cofinite is Damiani, Gigni, Tarska, I think.
And this is the most crucial part, right, of all this analysis.
Well, actually,
Otherwise, it's
you have to prove some coherence, but finiteness. But this finiteness, in terms of a family, or you have to wait because you also need to like consider the families of Riemann surface, and you prove some finiteness properties, the coherence of or the local freeness of these conformal blocks. I mean, you cannot just the most useful results cannot just be about one single Riemann surface. You can
Yes.
have consider families, and here is a finiteness result for the families. I would say that in the algebraic geometry setting is proved by Damiani, Gibney, and Tarska. And
for any
well, their paper they mainly deal with C2 cofinite and rational, but I think for the finite dimensionality they only need C2 cofinite. Yeah, but in the analytic set for analytic families, it's basically improved in my work collaboration with Hao Zhang's work. Yeah.
and that it gives you left exact factor.
This is almost wrong because the conformal block function is defined in terms of it's the vector space W mod something mod a action acting on W, the dual space. If you remove the dual space, you can say it's right exact. You take the dual space, it is the exact. Yeah, so the letter is quite trivial. Yeah. Okay, so the previous result is quite important. The result that the identification, the isomorphism between these two spaces are actually quite important because you need this isomorphism to compare. So there is we would expect that the categorical S transforms and the modular S transforms are equivalent. But if you want to prove that these two are equivalent, you first need to relate the VOA conformal blocks with the categorical model functions. So this gives so this isomorphism it is actually the first step for the comparison of the two S transformations. But now it's I guess so far our understanding of the category S transform is restricted to the finite tensor category, but not the modular GV category. Is that true? I guess yeah. So far, our knowledge is mostly on the finite, the rigid categories. But anyway, even in the rigid categories, this is still a new result, and it allows us to precisely formulate this control, and it allows us to proceed in the project of comparing the two S transforms. And this comparison of the two S transforms is also essential in the construction of the logarithmic full CFT. Because already in the rational case, when Huang and Kong they construct the rational full CFT, they already use the equivalence of the two S transforms to construct it. So it is reasonable to expect that in the logarithmic case, you also need this equivalence of the S transforms to construct the full CFTs. Okay, so this is the first half of my talk that shows you how the conformal blocks are related to the ends and the coends. And the second half, I will talk about the pseudo-traces. So what's the main difference between the pseudo-trace thing is that pseudo-traces are defined in terms of the associative algebra structures. If you only have these objects inside the VOA module categories or their distinct products, you don't know how to define a pseudo-trace. You need to consider some symmetric linear functions on certain associative algebras in order to define this this pseudo-trace. So that's what I will do in the remaining pages. So as I said, in order to relate the pseudo-trace to our work, we have to define this associative algebra structure. And what is the main new discovery of in our recent paper is that we noticed that this is this object. This is originally a V tensor 2 module. It is also an object in the link product, but this is not just a V tensor 2 module. This object itself has a associative C algebra. So this is actually not surprising because if you look at the rational case, I guess maybe, okay, let me. In fact, in the rational case, you see that this object as an end, it is the direct sum over all irreducibles of M tensor M prime. Okay, so each direct sum component has a canonical associative algebra structure, although not a unital structure, because this is when M is infinite dimensional. This algebra does not contain the identity map, so this is not unital, but still it has an associative algebra structure. So our main discovery is that this associative algebra structure still exists when you work with this non-semi-simple C2 cofinite VOAs. So next I will show you some
This algebra is infinite dimensional.
infinite dimensional. Yeah, I will show you how this associative C algebra is.
In what sense it is an algebra? It is an algebra in the category
No, it's over the vector, the complex field C. It's the just like this algebra. You consider, well, I mean, the easiest way is to consider M.
You take in irreducible objects from the category and you answering them in the category, right?
Let me give you an example. You consider a countable dimensional complex vector space, and you consider all finite rank operators. These form a associative algebra, but not unital because the identity map does not have finite rank. So this corresponds to one component. One component, each direct sum component, it corresponds to the algebra of finite rank operators defined on a countable dimensional complex vector space.
So you just take VOA representations, take underlying vector space.
Yeah, I take representation, but I mean, if you to define this, you don't really need the VOA action. You only need the gradient. You need the gradient to define the counter gradient, but that's all. I mean here. I mean, if you look at M tensor M prime, and if you want to define the product, the easy way is to take the contraction. Use the contraction to define the associative algebra structure. Okay.
So can you rephrase, but your category is finite, right?
Finite, yeah.
You could take equivalent category of representation of finite dimensional algebra.
Yes.
This is essentially regular bimodule, finite dimensional regular bimodule of that.
Bimodule of
a finite dimensional algebra realizing.
Yeah. But But here I'm working because but in that, if you work with finite dimensional algebra, then your vector space is finite dimensional. But here is infinite dimensional.
Yeah, but I'm just taking equivalent category.
Yeah.
It's
it will be.
Because it's finite category.
It will be kind of
finite dimensional algebra realizing that category. And then this.
Yeah, exactly.
I know.
Yeah.
The same look.
Which is same
It's not the
algebra.
same. The category of modules over VOE, so we look at them as great vector space.
No, I know.
Yeah, but it's kind of like a Morita equivalence.
By representations of an algebra, you will be known.
I can still do the same construction.
No, but
But it will be different algebra.
will be different algebra.
Of course.
Yeah, it's a kind of a Morita equivalent algebras.
It's not categorical.
Yeah.
It's
It's not categorical.
It's not categorical. Yeah, just like
That's the point.
So okay, so next page. So I will give you some rough idea of how the product in this associative algebra is defined. So basically, I want to define the product. I want to let this map to denote the product in my associative algebra. So the product, this product as a map is a map from box tensor C, tensor box tensor C to box tensor C. And it turns out that this map defining these products of this associative algebra is a conformal block. It is a conformal block of this type. So maybe I can this is maybe quite abstract, but I will give you a concrete example to give you some idea of how this kind of conformal block look like. For example, if you take the same geometric data, but you choose some simpler modules. So here, if you have 4 incoming mark points, and if you put M, V module, M prime, it's contragradient, M and M prime, and the output is you have 2 outgoing output points, and I put the M and the M prime. And what are some examples of conformal block of this type? The easiest one is the contraction. You use the contraction to define a map from this tensor product of 4 vector spaces to this one. So this map defined by the contraction is indeed a conformal block. It satisfies the definition of conformal block of this type. So you can, although I didn't show you the rigorous definition of conformal of this type, but you can imagine that this map has some invariance properties, and the same invariance property can be applied to this more general setting where this module is not M tensor M prime, but a more general V tensor 2 module, and this is also the box tensor C and the box tensor C, and this is also box tensor C. So basically, what I'm doing is I replace this with the more general one. Of course, if your module is rational, if your VOA is rational, then this is basically the same as this one. But anyway, you can see that there are some way to consider the conformal blocks of this type, which specializes to the map of this type. But I want to tell you what type of conformal block is this, but I haven't shown you how to define this particular conformal block that gives you the product of this associative algebra. It is actually defined in terms of the Sony factorization theorem. So let me show this in the next page. You consider the left-hand side, and I cut it horizontally. I cut it into the left-hand side. I have 2 copies, 2 components, and the right-hand side I have 4 components. According to the Sony factorization theorem, this conformal block could be written as the product of the left-hand side and a unique conformal block. And this conformal block is indeed the multiplication map of my associative algebra. So this is actually quite a little bit surprising, because we never expect that the associative algebras that arise from VOAs could be defined in terms of conformal blocks. But that's mainly because, like, for example, if you work with Drew algebras or higher Drew algebras, you consider finite dimensional space. You consider some truncations of the VOA module structures. But here I do not do any truncation. I work with the full VOA modules or bimodules. If you work with the full spaces, then the multiplication map could be realized by a certain conformal block. Okay, so I have this product, and in our paper we show that this is indeed it indeed satisfies the associativity, so that it gives you an associative C algebra structure, and as I draw it here, and it is rational, then this associative algebra structure agrees with the usual one defined in terms of taking the contraction.
In the level of the conformal block, I guess everything is depends on the space-time point. So how this space-time point dependence disappear and define associative
Okay.
algebra?
You mean like the, for example, if you look at this point, you can always choose a canonical choice of the. For example, you choose this one to be the CP1. You pick this one to be 0 and put this one to be infinity. In that case, you only need to care about the local coordinates, right? So I choose some canonical one for this one. This is the z. This is 1 over z. Then so this is more or less the canonical choice.
So you found the associative algebra inside the tubed Riemann surface, or I mean operand of the tubed Riemann surface, or
I mean, this is just over C, right? Associative algebra over C. I mean, is this no? I mean, if you work with operand,
if it depends on the space-time point, I think it's impossible to be associative. So somehow the space-time point dependence disappear in this construction, right?
I don't know, but maybe let's talk about this after.
Can I ask another question?
Yeah.
So generically, you end up in the completion of right-hand side.
Yeah,
but
yeah.
Here, not.
Good question. Here you don't need to worry about the completion. Why? Maybe this page is easier. You look at this. The conformal block satisfies some invariance property, which implies that the Virasoro operator L0 acting on this commutes with this map. So you can put it here and you can move this L0 operator to the right-hand side. So it means that if you put in a finite energy vector, the output will also be finite energy. So you don't need to worry about this computation. It works at least in the original space. Yeah. So you have this associative algebra, and you can use this. You can study the representative category of this associative algebra. And it turns out that if you use the previously defined dimensional transformations, when you can use this, you can show that this map, the dimensional transformation that we defined previously, is indeed an algebra homomorphism, which means that it actually defines a representation of my associative algebra box tensor C on the VOA module M. So it means that if you choose a VOA module M, so this vector space not only is a VOA module, and it's also a left module of my associative algebra box tensor C. Okay, so it means that, in other words, it means that you have a functor defined by sending M and its vertex operator to M, and the dimensional transformation defined by this vertex operator. And we actually show that this is if you define this category, you cannot consider the category of all left modules. You have to consider more reasonable modules, which are finitely general left modules that are quotient modules or free modules, because my algebra is not unital. So if your algebra is not unital, then not all left modules are quotients or free modules. So you have to restrict to these more reasonable modules and consider finite generated ones, which I call the coherent left modules. So it turns out that this gives us a linear isomorphism between these two linear categories. Okay, so this is quite important because it tells you that if M is, for example, projective on the left-hand side, if it is projected as a VOA module, then it is also projective as a box tensor C left module. Okay.
So you still need the mod V to be finite, right?
Finite, yeah, always have the finiteness. Okay, so now I can give you a.
So if it is finite, it's just a module category or some associative unit or not?
Yeah, exactly. Yeah, finite dimensional unit to associative.
So can you just reconstruct this finite dimensional unit, or is it just based version of it where the?
No, I don't think so. This.
Can you see it from your non-unital algebra, from big non-unital big algebra?
You may reconstruct the non-unital one from the unital one,
or the other way around?
Other way, I mean, other one is easy. You take the. This is just I'm going to say.
Okay.
You take a product generator and take the anamorphism algebra, and you get some particular choices of this algebra. But anyway, so let me first introduce the pseudo-trace construction. Actually, it's dates back to Arthur Stallings in maybe 70 or 60 years ago. But basically, if you ignore all these technical details, what this pseudo-trace construction, it gives you a canonical map from. Okay, I need to explain some of the notation. So M is A is a finite dimensional unitary algebra. M is a finite dimensional projective left A module. And in that case, you can define a map from the space of symmetric linear functionals on A to the space of symmetric linear functional on the anamorphism algebra of M in terms of the projective basis. Okay. And the most interesting case happens when M is a projective generator of A. In that case, you can we know that this pseudo-trace construction establishes a linear isomorphism between these two spaces. But in my talk, I will mainly focus on the infinite dimensional case. I will actually apply this result. I mean, I need to generalize this result to the setting that A is my non-unital infinite dimensional algebra. It turns out that this isomorphism is still true when you replace A with my box tensor C. In this box tensor C, you still, in fact, in some of my joint paper with Hao Zhang and another paper that are not listed on the slides, we have proof that for this box tensor C, you also have this isomorphism between these two spaces of symmetric linear functionals. If you take G to be a projective generator in my module category of B, and recall that I have this isomorphism of categories. So a projective generator on the left-hand side is also a projective generator on the right-hand side. Okay, so I have this SLF box tensor C, isomorphic to SLF box tensor CG, and
which is the same as a SLF of endomorphic algebra over the VOA modules. But anyway, what I want to say is that the right-hand side, this one, it's easy to show that the space of symmetric linear functionals on, the left-hand side, the space of symmetric linear functionals on my associated algebra is, you can easily show that it's isomorphic to the space of conformal blocks of this type. And using the solving factorization theorem, you know that this space of conformal block is isomorphic to the torus conformal block by composing this conformal block with a conformal block like this. With the canonical conformal block, swap tensor C, you compose this canonical one with that one, you get the isomorphism from this space to this space. So basically, you know that the left-hand side is isomorphic to the space of torus conformal block with a vacuum input. And so this isomorphism will show you that you have a canonical way of defining the, either using the pseudo-trace construction or using the solving factorization theorem, they give you the same isomorphism, which relates the space of torus conformal block with vacuum input to the space of symmetric linear functionals on the endomorphic algebra of the product generator. So this is our research result, which is conducted by Adat and Ingo. So to summarize, I have to return to the title of my talk. So how are coens related to pseudo-trace? So there are indeed a lot of technical details, but I think the most important reason that coens could be related to the pseudo-trace is that pseudo-trace, if you want to run a pseudo-trace machinery, you need to have associative algebras over a complex field. But how do we? So the key to this answer is that this end has an associative algebra. So you can apply the pseudo-trace machinery to this associative algebra to relate the coens, the end and coens to the pseudo-traces. So I think I shall stop here. So thank you very much.
Okay, thank you for good talk. Other questions?
The algebra structure on this associative algebra structure is coming from the canonical pairing of M dual and M, or it really has some.
It is an N, so in some way you can use M and N dual to get this. You mean associative? The associative algebra structure is kind of compatible with the VOA the V tensor 2 module structure. So
like if you introduce some filtration, then could you get the Z algebra? This algebra structure.
Actually, we conjecture that. So there is a paper by Tsuchiya and 2 other authors. They introduce a kind of regular algebra or something like that. They consider the original universal algebra, but they consider the general eigenspaces of L0, the 2 copies of L0, and they show that this subspace also has an associative algebra structure. We actually conjecture that our algebra is isomorphic to theirs. So probably their approach could give a better answer to your question.
Yeah, I see. Yeah. Thank you.
Are there other questions? What do you think personally? This associative algebra is easy. It's easy to understand representation theory of VOA. Can I tell you something more about representation theory of my VOA?
You mean for some explicit VOA?
Yeah, like take any VOA. Do you have example of such associative algebra?
I don't think beyond rational VOAs. I don't think for other non-rational.
Let's take some fermions and write this out.
But even rational, take loop groups.
Yeah.
Is it somehow related to a space of functions?
Well, I can only.
Let's take Ising. Ising VOA. Yeah. What can be?
And let's make it.
What is this? What is this associative algebra?
You mean that it's really more explicit in that one?
Yeah, just right. Yeah, the joint relations. Yeah. Can I use it to study representation theory of VOA, or it's?
Yeah, maybe using just to talk, we could take A1 level 1, so SU2 level 1.
Or SU2 level 1.
I think you should maybe think of.
No, that's too big. That's too big. This algebra is too big to give you some explicit information.
Okay.
Matrix blocks, and you just have to the dimensions.
So for easing, right, you would have three simples, and so then that representation series recovered if they're basically like three infinite features.
Yeah.
No,
Yeah,
because they
They're not just matrices, they're matrices of
infinitely many
finite
matrices.
rank. Yeah,
No, because it's a
finite
great
rank.
bicycle.
Basically, three matrix algebras. If you have three irreducible, then basically there are some of three matrix algebras, but not containing the identity.
Yeah, the infinite dimensional matrix algebras.
Yeah. Basically, it's
But this is a condition, right? They are the endomorphisms of graded duals.
yeah.
So they are finite rank.
No, what?
Are they
Gradient
finite
space are finite.
They're matrices of finite rank.
Yeah.
Infinite size, but finite rank, right?
Oh, you mean on the gradient
So
space?
each summand, like what?
Each-
what
No,
you
each summand is still. So this is a finite sum.
Yes, but each M is an
Each M is infinite dimensional.
interdimensional, but with graded components.
Gradient
defined.
component, yeah.
And then you look at the matrices which preserve the gradient, right?
Yeah.
The morphisms which preserve the gradient.
Yeah.
But why don't you have the identity and the morphisms there?
But does
I mean, I do think you have to consider all. I mean, you view this as a subspace of the. You consider this part as inside the space of all linear maps on M. Then this certainly does not contain the identity because basically this only gives you.
What is the condition which
So the condition is that it has to the range should be finite dimensional. The range you have to consider the endomorphism of M which have finite dimensional, which finite ranks. You have to consider finite ranks.
only finite rank?
Not arbitrary linear maps.
So where does this finite rank condition come from?
From the
Well, it comes from because the range is always so
because
if you pick one element.
It has to be tensorflow.
Yeah.
Okay, so makes sense.
But we are teaching.
Sorry. Is a natural way to complete this matrix and get the Honneim algebra which should be corresponding to somehow conformal net?
I mean, have the you need the unitarity.
Yeah.
but-
If you
but
actually
basically in this way, well, of course, but that's not interesting. I mean,
Okay.
Yeah.
Yeah. I see. So no natural way to.
Yeah, at least for in beyond rationality, there's certainly no natural way to
Yeah.
complete it.
I see.
Modules which are
So we know Rybachenko coend is at least in the category, it's a coalgebra.
Yeah.
Is it related by some duality, this coalgebra to this algebra?
Exactly. It's the co-algebra structure is indeed related to the algebra structure of this one. It's not so obvious. It's related.
So, just ask you, just say that the coalgebra of coend.
The co-algebra structure is related. Yes.
Yes.
So it makes sense.
So what we find amazing is that if you have a non-semi-simple VOA, non-rational VOA, but still finite, so you just take this matrix algebra, finite rank operators.
Yeah.
So there's still like finite number of summands, maybe an integral.
Yeah.
But how do you get something non-semi-simple out of these things?
I mean, if you just have this one, you certainly cannot get anything.
But he has a coend, right?
Yeah, so coend will be only interesting maps between these different matrix algebras, right?
Yeah. I mean, even if you pick any associated finite
there will be some non-symmetric. It will be something.
Some interesting diagram of this.
But and it will be some subalgebras in matrix algebras. In matrix algebras, we have very many subalgebras because it's and.
Yeah.
So in matrix algebra, we have many non-semi-simple subalgebras. That's why. Okay. Very good. Thank you. Okay.